Hey everyone, welcome to all the KOEIGO STEAM parents. We are so excited to have you joining us as your kids get started on this awesome STEAM journey at OCSI. This week, they're going to be diving into the world of traffic signals. Might seem kind of simple at first, but trust me, there is so much cool science and technology packed into those red, yellow, and green lights.
It's true. We're going to give you the inside scoop so you can follow along with what your child is learning. Just last week, they were working with parallel circuits. They even got to use multimeters to measure voltage and current, just like real engineers.
Absolutely. And they're not just messing around. They're recording all their findings in those Arduino workbooks. They're applying Ohm's law, VIR. Remember that from physics class.
And what's really cool about Ohm's law is that it governs how electricity works in any circuit. Like, it's the basis for everything, from simple circuits to the more complex traffic signal they're going to be designing this week.
Okay, so for those of us who haven't thought about Ohm's law in a while, could you give us a quick refresher?
Sure. Think of voltage, V, as the pressure pushing electricity through a circuit, like water through a pipe. Current, I, is the amount of electricity flowing. And resistance, R, is anything that slows that flow down. So Ohm's law basically tells us how these three are connected. Like, higher resistance means lower current for a certain voltage.
So when we talk about resistors, those little components in the circuit, we're basically talking about adding resistance on purpose to control that flow, right?
Exactly. That's crucial when you're working with things like LEDs. Too much current and poof, they could fry.
Oh, wow. So the resistors are kind of like safety valves, protecting the LEDs so they can shine bright without burning out. It's pretty amazing how these basic concepts are the foundation for something as complex as a traffic signal.
It really is. And this week's challenge is all about using what they know about circuits to design a working traffic light using Tinkercad. Tinkercad is this incredible software. It lets them build and test their designs virtually before they even have to touch any physical components.
So it's like a digital sandbox. They can experiment and try things out without the risk of, well, blowing anything up. But then the real magic happens when they take that Tinkercad design and turn it into a real circuit. What are some of the main parts they'll be using?
Of course, you've got the LEDs, red, yellow, and green, to make the traffic light. But the brain is the Arduino board, a tiny computer they can program to control those LEDs. And to make it interactive, they'll also add a push button to mimic a pedestrian crossing.
Okay, so someone presses the button, it sends a signal to the Arduino, and it has to decide what to do with that information based on the code they wrote. That's where things get really interesting, right?
Absolutely. It's a really cool way for them to learn about how software and the physical world interact. And to do that, they'll need to understand a key difference in electronics: digital versus analog signals.
Okay, I've heard those terms. But can you explain what they mean in this context?
Sure. Think of a light switch. It's either on or off. That's a digital signal. It's like a 1 or a 0 for a computer. But then think of a dimmer switch. You can gradually change how bright the light is. That's analog, a range of values between on and off.
So LEDs, they're either on or off, that's digital, but the code that controls them is also digital, right?
Yeah, you got it. And what's really neat about Arduino is it can work with both types of signals, digital and analog. It gives them a lot of options when they're building things.
That is cool. But I bet writing code can be pretty tough, especially if you're just getting started. How are they tackling that?
One helpful technique is called pseudocode. It's basically writing out the program steps in plain English before you get into the actual programming language.
Oh, I see. So instead of trying to figure out the exact code right away, they can focus on the logic first, like turn on the green light, wait 5 seconds, turn on the yellow, and so on. It's kind of like making an outline before you write a story.
Exactly. It helps them think through the problem step by step. And then once the logic makes sense, they can translate those steps into Arduino code.
This all sounds so hands-on and fun. I can already picture those little LEDs blinking as they try out their designs.
It's really exciting to see them bring their ideas to life. And what's great about this project is it's not just following instructions. It's about figuring things out, like problem solving, debugging, and trying things out over and over until they get what they want.
Speaking of debugging, and I know that's a big part of programming, how are they learning to handle those coding errors?
Debugging is all about being a code detective. Sometimes it's a simple mistake, like a missing semicolon. Other times it's a problem with the logic of their code. The Arduino IDE actually has some pretty cool features. It highlights those syntax errors, and it lets you run the code line by line so you can see what's happening at each step.
So it's not just about fixing the error, it's about understanding why it happened and how to avoid it next time. That's a skill that goes beyond just programming, don't you think?
Absolutely. It's about critical thinking and problem solving, which are super important for anything you do. And one thing that makes this traffic light project really engaging is that it comes from a real-world challenge, designing a system to manage traffic flow. It's something we see every day, but don't really think about how complicated it is.
It really is a great example of how something so simple can actually involve a lot of design and engineering.
Yeah.
I bet there's a pretty interesting history behind traffic signals, how they came to be.
Oh, there is. But before we go back in time, let's take a closer look at one of the key components they'll be using, the push button. It might seem like a basic on-off switch, but there's actually a lot more to it.
Okay, I'm interested. What are some of the nuances of using a push button in this project?
Well, first they need to understand that the push button is an input device. It sends a signal to the Arduino when you press it. That signal needs to be clear and consistent. And that's where something called a pull-down resistor comes in.
Pull-down resistor? That sounds a bit technical. What does it do?
Think of it as a safety net. It makes sure the Arduino doesn't get any wrong signals when the button isn't being pressed. It helps prevent those moments when the traffic light starts acting weird for no reason.
Ah, so it's kind of like a behind-the-scenes thing, making sure the push button works correctly.
Yeah.
It's amazing how even the smallest parts can be super important.
It is. It's a good lesson in paying attention to details and how even basic circuits can have hidden complexities.
So those push buttons are sending signals to the Arduino. But how does the Arduino know what to do with those signals? That's where the code comes in, right?
Exactly. And this week, they're learning about a key idea in programming, conditional statements. Specifically, they're working with if statements. These let the program react differently depending on certain conditions.
So it's like saying to the Arduino, if this happens, then do that. Otherwise, do something else.
Precisely. In the case of the traffic light, the code might say something like, if the push button is pressed, then flash the green light for pedestrians. Otherwise, just keep doing the normal red, yellow, green sequence.
Oh, okay. So it's like giving the Arduino a set of rules so it can make choices based on what's going on.
And to make those decisions, the code has to be able to compare values
Yeah.
and figure out if a condition is true or false. That's where comparison operators come in. They're symbols like for is equal to, for is not equal to, for greater than, and so on.
So by combining those operators with different values and variables, they can create all sorts of conditional statements to control how their program works and what it does.
Exactly. And this is just the start of their coding journey. As they learn more, they'll discover more complex conditional structures and logic operators, which will let them create even more sophisticated and interactive programs.
It's amazing to think about all the possibilities they're unlocking with every new concept. And it all starts with that basic understanding of circuits. Which brings us back to the traffic light project and how it's used in the real world.
Speaking of which, I think it's time to dive into that fascinating history of traffic signals we were talking about. You know, it's crazy to think that the very first traffic signal was invented all the way back in the 1860s, before cars even existed.
Wow, really? That long ago? What did it look like?
Well, it was meant to control horse-drawn carriages and pedestrians in London. It was nothing like the systems we have now. This first traffic signal was actually operated by a police officer using gas lamps to show the signals.
So not exactly the most efficient setup. I can see why that didn't last very long.
Yeah, you're right. And on top of that, it was actually considered pretty dangerous. There was a gas leak that caused an explosion just a few weeks after it was installed.
Oh no, that's terrible.
It was a major setback for traffic signals, and it took quite a while for people to revisit the idea. But as cars became more common, the need for traffic control grew, and this led to a bunch of new inventions in the early 1900s.
I bet those early traffic signals were pretty different from what we're used to seeing today.
Oh, absolutely. In 1910, the first automatic traffic signal was put in place in the United States, but instead of lights, it used signs that switched between stop and proceed.
So still a bit clunky compared to the red, yellow, and green lights we have now.
That's right. But just a few years later, in 1912, red and green lights finally made their appearance. It was a big jump forward in traffic signal design.
Yeah, I bet those visual cues made a huge difference in terms of clarity and safety.
You bet. And then in 1923, an amazing African-American inventor named Garrett Morgan, he patented a design for a traffic signal that used a three-position system. This added the yellow caution light, and that gave us the system we use today.
Yeah, that's incredible. It's really inspiring to hear about his contribution to something we use every day.
It really is. And his story is a reminder that innovation can come from anyone, anywhere, and that having diverse perspectives can lead to amazing breakthroughs that benefit everyone.
Absolutely. Speaking of innovation and problem solving, let's get back to our KOEIGO students and the challenges they're facing in designing their own traffic lights. We talked about debugging, but what are some other roadblocks they might hit?
One common challenge is understanding how electricity works differently in series and parallel circuits. Remember we talked about those last week when they were building those simple circuits? Now they need to apply that knowledge to this more complex traffic signal design.
Okay, right. So could you give us a quick recap of the difference between series and parallel circuits and why it matters for this project?
Sure. Imagine a single line of people all in a row. That's like a series circuit. If one person stops, the whole line gets backed up. Same thing in a series circuit. If one component fails, the whole thing stops working.
And I remember you said a parallel circuit is more like having multiple lanes of traffic.
Exactly. If one lane is blocked, the others can still keep moving. In a parallel circuit, each component has its own path for the electricity. So if one thing fails, the rest can keep working.
So for the traffic light, they're probably using a mix of both, right? Each LED needs its own pathway, but within that pathway, there might be other components, like resistors connected in series.
You got it. And understanding how to use these two types of circuits together is super important to get the traffic light working the way they want it to and make sure those LEDs light up correctly.
So as they're building their circuits on those breadboards, they really need to be thinking about those pathways and how the electricity is flowing through them. It's more than just connecting wires.
It definitely is. And another thing they'll need to figure out is how to choose the right resistors to protect the LEDs. Those resistors help control the amount of current flowing through each LED so they don't burn out.
Right, like a safety valve, we talked about that?
Yeah.
But how do they know what kind of resistor to use?
That's where Ohm's law comes in again. They need to know the LED's forward voltage, which is basically how much voltage it needs to turn on. Then, using Ohm's law, they can calculate the right resistor value. This ensures the LED gets the right amount of current.
So it's kind of like a delicate balancing act, making sure there's enough current to make the LED bright, but not too much that it burns out.
You nailed it. And they're not just picking random resistor values. They're actually using Ohm's law to make informed decisions, just like real engineers.
It's pretty cool how these circuits that seem so basic actually need a lot of planning and calculation. I'm starting to see traffic lights in a whole new way.
Me too. And speaking of seeing things differently, they're also learning about another important distinction in electronics this week, the difference between digital and analog signals.
Right, we talked about that before with the light switch and the dimmer switch, but how does that apply to the traffic light project?
Well, the LEDs are digital components. They're either on or off, like that light switch. But the Arduino board can also work with analog signals. Those signals change continuously, like the dimmer switch.
So even though the traffic light seems totally digital, red, yellow, green, there's actually room to add analog stuff too.
Exactly. Imagine a traffic light that slowly brightens and dims instead of just switching suddenly between colors. That would need analog signals to control the LEDs. And the Arduino can do that.
Oh, wow, that's really cool. It opens up a lot of possibilities for creating more subtle and interesting effects.
It does. And as they learn more about electronics, they'll find more and more uses where both digital and analog signals work together to create really complex systems.
So it's a really fundamental idea that sets them up for all sorts of cool projects down the road.
Absolutely. And speaking of future projects, let's shift gears for a bit and talk about some of the tools they're using to actually build these traffic lights. We talked about Tinkercad, that awesome software that lets them create and test their circuits virtually. But what about when they want to build a real physical version?
Well, I remember seeing pictures of those colorful breadboards with all the wires and components. Those seem to be a big part of the process.
Yeah, they are. Breadboards are like the construction zone for electronics projects. They let students connect components without soldering, so it's easy to experiment and change things as they go.
It's kind of like a giant customizable Lego set for electronics.
Exactly. And what's great about breadboards is that you can actually see the circuit, which helps a lot with understanding how everything's connected and figuring out any problems that come up.
So it's not just about plugging things in randomly. It's about making a neat and organized layout that matches how the circuit's supposed to work.
Precisely. And that focus on detail is a really important skill, not just in electronics, but in anything where precision and organization are key.
Yeah, I can imagine those breadboards can get pretty crowded, especially when they start working on more complex projects. Are there any other tools they use to manage all of that?
One super important tool is the multimeter. It's a handheld device that can measure different electrical things like voltage, current, and resistance.
So it's like a Swiss Army knife for electronics.
You got it. And in their experiments, students use multimeters to take readings from their circuits. This helps them confirm their calculations and see how electricity works in real life.
So it's not just theory. They're getting hands-on and testing their understanding through experiments.
Precisely. And by comparing what they calculate with what they actually measure with the multimeter, they're getting a much deeper understanding of how these principles work.
You know what's really cool about all of this is that they're not just learning about electronics from a textbook. They're connecting it to a real-world problem that they can relate to, designing a traffic signal that could actually be used on the streets. I bet that makes learning a lot more fun and engaging.
Absolutely. It's one thing to read about circuits and coding, but it's totally different when you're actually building something real and tangible that could have an impact.
Speaking of impact, I'm curious about the coding side of things. We talked about conditional statements and comparison operators, but what are some other coding concepts they're learning that will help them bring their traffic lights to life?
One essential concept is working with variables. A variable is basically a container that can hold a value, and those values can change while the program is running.
Oh, okay. So it's like giving a label to a piece of information that the program can use and modify.
Exactly. For example, in their traffic light code, they might have a variable called green light delay to store how long the green light should stay on.
And then they can use that variable in their conditional statements to control the timing of the lights.
Precisely. And being able to work with variables is crucial to create programs that are flexible and dynamic, programs that can respond to different inputs and conditions.
It's like giving the program a memory and the ability to adapt to different situations. Pretty cool stuff.
It is. And as they get more comfortable with variables, they can start exploring even more advanced coding techniques, like loops and functions. These let them create more complex and efficient programs.
It sounds like they're building a strong foundation in programming that will be useful in all kinds of STEM fields, not just electronics.
Absolutely. And the skills they're learning, things like problem solving, logical thinking, creativity, attention to detail, those are all transferable skills that they can use in any career.
It's amazing to see how they're progressing and how these small steps are actually huge leaps forward for them.
It really is. It's an honor to be a part of their learning experience and see their enthusiasm.
Speaking of enthusiasm, I'm eager to hear more about the history of traffic signals. We left off with Garrett Morgan's incredible invention in the 1920s. What happened next in the evolution of this technology?
Well, after Morgan's three-position traffic signal became popular, there was a period of refinement and standardization.
So it was all about making the system more reliable and consistent in different places.
Exactly. And as traffic got heavier, new challenges came up. This led to even more innovations like traffic sensors, computer-controlled systems, and even smart traffic lights. That can change based on real-time traffic conditions.
Wow, it's fascinating to see how technology has kept up with our increasingly complex transportation systems.
It really is. And speaking of evolving technology, let's zoom in on another tool that's super important in both electronics and computing: the keyboard.
The keyboard. It seems pretty basic, but I'm guessing there's more to it than meets the eye, especially for programming.
You're right. The keyboard is how we mainly talk to computers. So knowing how to use it well is super important for anyone who wants to learn coding.
So beyond just typing words, how do they use the keyboard in programming?
Well, a lot of programming languages use special characters and symbols that you can't just find on the regular keyboard layout. That's where the Shift key is handy.
Ah, so if you hold down Shift while pressing certain keys, you can get those special characters and symbols that have specific meanings in code.
Exactly. For instance, in the Arduino IDE, the Shift key is used to make some of the symbols used in comparison operators, like the less than and greater than symbols.
So it's essential for building those conditional statements that control how their traffic lights work.
Precisely. And besides special characters, they use the keyboard to move around the code, edit text, run commands, and a lot more.
That's like the control panel for the whole coding process.
Exactly. And as they get better with the keyboard, it almost becomes like an extension of their thoughts. They can turn their ideas into code quickly and accurately.
It's amazing how something as everyday as a keyboard can be such a powerful tool for creating and innovating.
It really is. And speaking of creating and innovating, let's get back to the traffic light project and talk about some of the design choices students are making as they build their virtual prototypes in Tinkercad.
Okay, so they're not just copying a standard traffic light. They actually get to be creative and explore different designs and features.
Absolutely. One of the first things they have to decide is how to arrange the LEDs, Will they do the classic vertical stack of red, yellow, and green, or try something different?
I'm sure some of them will come up with some really cool ideas.
Definitely. And beyond just the basic layout, they might also think about adding extra features, like pedestrian crossing signals or even sensors that detect cars, and adjust the timing of the lights automatically.
So they're not just building a static model, they're thinking about how to make their traffic lights interactive and responsive.
Exactly. And that design thinking process is a valuable skill in itself. It encourages them to think about what the users need and how to create solutions that really work.
It's like they're little urban planners tackling real-world traffic challenges.
You got it. And as they keep working on their designs, they learn how important it is to test, evaluate, and refine their ideas until they get something that really works well and meets all the requirements.
It's a lot like how real engineers and designers work, constantly improving and making their creations better.
Exactly. And speaking of improving things, there's another important concept in programming we should talk about: code optimization.
Code optimization, what's that?
It's about making your code more efficient and streamlined without changing what it does. Think of it like decluttering and organizing your code, so it's easier to read and runs faster.
So it's not about changing the outcome, it's about making the code run more smoothly and efficiently.
Exactly. And while the Arduino IDE does a lot of this automatically, it's still really good for students to understand the basics of optimization.
Why is that? What's the benefit of writing optimized code?
Well, for one thing, optimized code usually runs faster. This is super important for things where speed matters, like controlling systems in real time or for games.
Makes sense. And I bet it also helps save memory and processing power, especially for those bigger, more complex projects.
Exactly. And maybe even more importantly, optimized code is usually easier for people to read, understand, and change.
So it's not just about making the computer happy, it's also about making the code more understandable for humans. That can be a big help when working together on projects or revisiting old code.
You got it. Learning how to optimize code is a valuable skill that will help them as they keep learning about programming.
It's like a lesson in efficiency and elegance, which are good qualities to have in anything you do.
Absolutely. And as we wrap up this part of our conversation, it's worth remembering that the things students are learning in this traffic light project go way beyond just electronics and coding.
What do you mean?
Think about all the problem solving they're doing as they work through those circuits and fix their code. Think about how creative they're being as they design their traffic light prototypes. And think about the teamwork and communication skills they're building as they work together and share their ideas.
You're right. These are essential skills for the 21st century
Yeah.
that they can use no matter what they choose to do in life.
Exactly. And that's one of the most exciting parts of STEAM education. It's not just about technical skills, it's about encouraging a love of learning, creativity, and innovation. That will help them succeed in a world that's always changing.
Well said. Now, before we move on to the last part of our deep dive, I'm curious to hear more about the Arduino IDE, the software they're using to program their traffic lights. How does it actually work?
Great question. The Arduino IDE is a powerful but easy-to-use platform. It has everything students need to write, upload, and manage their code. Let's take a closer look at some of its key features. The Arduino IDE, it's basically a software environment where they can write their code. They use a language that's based on C++ or PE, which is a popular programming language used in all sorts of things. It has a text editor where they actually type the code, a compiler that translates that human-readable code into instructions for the Arduino, and a way to upload that code to the board.
Oh, okay. So it really streamlines the whole process from writing the code to actually seeing it work. It's like their programming headquarters. What are some things that make it easy for beginners to use?
Well, one helpful thing is syntax highlighting. As they're typing, different parts of the code, like keywords, variables, and comments, they're shown in different colors, so it's easier to spot mistakes and see how the code is structured.
So it's like having a built-in code checker.
Yeah.
That helps catch those typos and things that could cause problems later.
Exactly. And the IDE also gives them hints and suggestions as they type, making it easier to find the right commands and make sure the syntax is correct. Plus, it has a library of pre-written functions, which are like little reusable chunks of code that do specific tasks, saving them a ton of time.
So instead of having to start from scratch every time, they can use these existing functions to build their programs faster. Kind of like having a toolbox full of ready-made parts.
Perfect analogy. And speaking of building things, let's go back to those breadboards. They're great for trying out circuits, but you wouldn't use them for a permanent setup, right?
Right. So what do they do when they're ready to make a more permanent version of their traffic light?
That's where soldering comes in. It's a way to join electronic components together using a melted metal alloy called solder. Kind of like welding, but much smaller and with a lower temperature.
So instead of just plugging things in, they're actually making those connections permanent.
Exactly. Soldering takes a bit more skill, but it makes the circuit much stronger and more reliable.
Oh, I see. And that makes sense for something like a traffic light. It needs to work outside and keep running for a long time.
Absolutely. And speaking of reliability, there's another key concept in electronics: continuity.
Continuity. I think we mentioned that earlier.
We did. Continuity just means that there's a complete path for the electricity to flow through the circuit, like making sure the road is clear for those little electrons to travel.
So if there's a break in the path, a loose wire or something, the circuit won't work right.
Exactly. And the multimeter can help test for continuity. It sends a tiny current through the circuit and shows whether or not there's a complete path.
So it's like a detective tool, helping find those hidden breaks that could be causing problems.
Exactly. As students get more experience building and testing circuits, they'll learn how important continuity is and how to use a multimeter to make sure everything's connected properly.
It's kind of like electronics and detective work go hand in hand. You need to be observant and put the clues together to solve the problem.
I like that. And speaking of solving mysteries, have you heard about one of the most famous mysteries in computer history? The story of the first computer bug.
Oh, yeah. Grace Hopper and the Moth. Right. That's a great story about how tricky debugging can be.
It is. Back in 1947, Grace Hopper, this amazing computer scientist, she was working on a giant computer called the Mark II. One day, it stopped working, and after a lot of troubleshooting, they found the problem was a moth stuck in one of the computer's relays.
A real bug in the system. You don't see that happening too often these days.
Not likely. Back then, computers were a lot bigger and easier for things to get into. Hopper and her team took the moth out and taped it in their logbook. They wrote, "First actual case of bug being found."
Wow. So that's where the term bug came from. We still use it today for any errors in software or hardware.
Yep. It's a good reminder that even with really complex systems, unexpected things can happen. And it shows how important it is to be really observant, troubleshoot carefully, and have a sense of humor when you're dealing with tech problems.
Speaking of challenges, one of the best things about this traffic light project is that it helps students see how hardware and software work together. They're not just building something physical, they're also writing the code that makes it come alive.
You're right, that connection between the physical and digital is everywhere these days. With the Internet of Things, smart homes, and all these connected devices, knowing how to make those two worlds work together is going to be so important in the future.
Absolutely. So as we wrap up our deep dive, what are some key things you hope parents will take away from this week's project?
I hope they'll get a better sense of how complex and clever something as simple as a traffic light really is. It's a great way to see how STEM ideas are used in real life, and it shows how creative and resourceful their kids are becoming.
I totally agree. It's also a great chance for parents to get involved in their child's learning, ask them about their projects, maybe even talk about careers in STEM fields.
That's a great point. Who knows, maybe this project will be the spark that ignites a passion for engineering, programming, or inventing. Who knows what they might create in the future?
Here's to bright minds and an even brighter future. Thanks for joining us on this deep dive into the world of STEAM. Until next time, keep those circuits buzzing.